Keynote. So with Guillaume, we are going to basically try to give you the some ideas about why we have developed SIMBA, where we are today, what are the new features that we're releasing in SIMBA today, and where we want to go.
Yeah, thanks a lot, Manuel. So, yeah, first of all, we would like to start by explaining why we're developing SIMBA. Because if we look into nature, after all, isn't there already enough simulation software out there? So, to show you this, let's consider a power converter design process. So, even if there are plenty of design processes, they're more or less share all the same pattern, and they can be usually divided in three different phases. An analysis phase at the component level in order to characterize the commutation shell. That is to say, to design the gate driver, to study electromagnetic compatibility, the PCB layout, and consider interactions between all of these items in each order. So in this phase, engineers only rely on tools such as spy simulation or prototype characterization and such as double cross test. A second phase is an analysis at the system level to integrate the power converter in its environment, such as a motor, a battery, or the electrical network. So the goal of this phase is to design the control to consider the thermal management, for example, or the magnetic components. In this phase, engineers use system-level simulation software such as MATLAB Simulink or hardware-in-the-loop tools. And finally, we have a third phase dedicated to test and validation. This is here we conduct a range of tests, including fault testing, log profile testing, and range estimation. So engineers, for this phase, engineers use hardware tools or more often experimental validation on prototypes. So here is the bottom line of all of this. We believe that today's the hardware development process looks like how software was developed 25 years ago. And because we often use slow single-thread calculations, we don't have systematic change tracing or automatic testing, and we usually rely on manual processes. And every time a requirement changes, we are forced to repeat large parts of the process. Though this is why we see here a real need for innovation in power converter development and why we are building SIMBA.
Oh yeah, so again, SIMBA is not about just being another simulation tool that is faster and more accurate. Our goal in SIMBA is basically to simplify, to accelerate, and to streamline the power converter design process. So our ultimate goal with SIMBA, I don't say that we are there yet, but our goal is to provide a unique platform where everything is streamlined. So all type of simulations, all type of test and report generation. And in order to do this, we have two strong foundations. The first one is a state-of-the-art simulator. We have an extremely fast now SPICE solver. We're going to talk later about that. And also the solver of SIMBA is excellent for system-level simulations. We have a simple and sleek graphical user interface. We have libraries for everything you need, electrical, control, thermal, mechanical, magnetics, and so on. And for motor drives, we have Unix, extremely accurate finite element analysis based motor models. So this is the first foundation. The second foundation, and it's actually more important than what you will initially think, is that we have in SIMBA unique scripting capabilities. We have, and I think we are almost the only one to have a native Python library that supports both multiprocessing and cloud computing that we can use for all sorts of automation, for optimization algorithm, and also for machine learning and artificial intelligence, like we will see later today with Alejandro. And that support as well automatic testing and report generation. So to summarize, the goal of SIMBA is first to simplify and accelerate the design process by reducing tool switching, and also by providing this simulation platform that is as accurate as possible. We reduce the need of physical prototypes and hardware-in-the-loop simulation. We basically want to have a platform where we have a digital twin, and that will basically cut down the needs of physical prototypes and hardware-in-the-loop simulation. We still believe prototypes are and samples are, of course, useful and are required. But if you do the simulation correctly, and if you do this process in a professional and in a thoughtful way, then you will need less the need of prototypes.
Yeah. And to show you this and to show our willingness for providing such a software, here is a look at the SIMBA release history. So since our initial release in 2021, that's only a little bit than 3 years ago. Um, Here you can see that we have continuously added features to enhance SIMBA capabilities, such as thermal analysis in February 2021, AC sweep a few months afterwards, and the capability to import pattern schematics, for example. So all of these features which were added represents our commitment to continuous development, which is always driven by user feedback and collaboration, ensuring SIMBA stays at the cutting edge of parametric simulation. So today, we are happy to release SIMBA 2024-11 that includes the compatibility with semiconductor SPICE models from manufacturers' vendors. And now, Manu is going to tell you a little bit more about this new release.
Yeah, so we're very happy that we release this today. So we release it first in a preview release. So if you have a SIMBA account, you can just go to simba.io and you can start downloading it. We will release the final release in a few weeks, probably in 2-3 weeks. We just want to make sure that some users starts to play with it and that it's a bug free. And the big feature of this release is the compatibility with SPICE model from manufacturer. And we are going to illustrate and to give you an example with Guillaume in a few slides. But before that, I want to cover quickly motor drives and why we think that SIMBA is the ultimate platform for electric drive unit simulation and design. When an OEM or when a company needs to build motor drives, it involves a lot of analysis and a lot of simulation on the thermal, on the transient, on the EMI, EMC, the range, the harmonics, the lifetime, the reliability, and so on. And all those analyses requires different models for the semiconductor and for the motor. And in SIMBA, we have different models of semiconductors. We have first idle models that are super fast and that can you can use them to simulate your control exactly like you will do in tools like Simulink. But you can complement them with thermal description files that sometimes are called as well Plex thermal description files. So you can load them in SIMBA and you can have super fast thermal simulation in SIMBA. And finally, as we said, we are now able to simulate SPICE models from vendors. So basically, you can decide your level of accuracy for the semiconductor while staying on the same tool. Same thing for the motor. We have our native SIMBA model that is good and fast, that support nonlinear, basically saturation. But we can have a lookup table-based model that takes into account things like spatial harmonics, advanced loss model in the motor. And if you want to go, we can also do like full co-simulation with FEA-based motor to have like extremely accurate uh, um, uh, um, model. So you can, and basically it's up to you, the user, to select the level of accuracy that you want. Of course, if you go down here, the simulation will take more time, but while the accuracy will increase. But since you can distribute the calculations on multiple cores, then it's less, it's less an issue.
Yeah, and to illustrate this, here is a typical example of what can be achieved with SIMBA, combining the power semiconductor switch model based on thermal description and the motor model based on the lookup tables from GMarget. So with these two models, SIMBA is able to compute losses of both power semiconductor switches and no motor, which will allow the designer to get the global influence of different parameters, such as the switching frequency, for example, or the modulation strategy. And with these two features annotated with the scripting and the parallel computing capabilities of SIMBA, this allows the designer to get an efficiency map that you can see here, sorry, and to get this efficiency map of the whole motor drive in less than 5 minutes. So this gets room to perform multi-objective optimization on both motor geometry design and inverter design.
Thank you, Guillaume. Let's go back to the SPICE compatibility. And I want to clarify a few things. So first, SIMBA is not a SPICE tool, and we do not intend to compete with any existing SPICE tools. That would be stupid. You know, you have tools that are free, LT SPICE, Q SPICE, that are actually pretty good. So we don't intend to compete with them. But basically, SPICE syntax and SPICE models is a standard now for semiconductor models. And if we want to build this unified simulation platform, we have to support them. You know, all the manufacturers, well, maybe not all, but most of the manufacturers, so Infineon, Wolfspeed, and so on, they provide the two things. They provide system level models, Plex thermal description files, and we can read them. And they also provide SPICE models for detailed analysis, and we support them as well. So this is not co-simulation, and this is not model translation like other tools do. We actually have modified the SIMBA solver to support SPICE syntax on top of what we have already, the control, the piecewise linear models, the idle models. So you can have a model where you have the thermal model, you can have the SPICE model, you can have the control with C code, you can also have some advanced motor models. So it's not a pure SPICE, it's actually better than this. And we have validated our tools with models from Infineon, Wolfspeed, ROM, and EPC. We would like to have some users trying to play with it just to continue a little bit the validation, but so far we have kind of good feedbacks from our test. So to illustrate this, Guillaume is going we are going to give you an example, a real life example of what we can do with that.
Yeah, thanks, Manu. So, but first of all, let's say a few words about the context. Let's imagine that we have to consider the early stage design phase where we need system level models. In this system level models, we need fast simulation time to have a look at different fields. It can be the magnetics, but it can also be the control, and of course the thermal losses. So in such cases, detailed model of power switch, such as SPICE models, are not suitable because they are too much time consuming. And we currently use ideal models associated with loss data table, that is say the thermal description file, based on the data sheets of the manufacturers. But here is a question which can be raised. How to do if the power switch loss data are not available are suitable. Indeed, we might want to get the power switch loss data in custom operation mode, which can lead to very different results than the one from the classical double bus tests. For example, if we want to compute the losses of device in their test with another complementary switch than the one of the double bus test, it's well known that its recovery loss will have a great impact at the turn on of our device in their tests. Or if we want to consider the roll value of heuristic elements of the PCB or bus bar, such as the leakage inductor of the switching loop, which has a great impact on switching losses, both at turn on and turn off. Or again, if we want to compute switching loss in zero voltage operations, such as in dual active bridge or LLC topologies, we'll speak about that later, as they will overestimate the turn-off losses. Well, it means that there is a challenge to get loss data in many operation modes that are different in the double bus test. So here is the question: how to get this custom loss data? Manu, do you think that you can explain us how it is possible with SIMBA?
Sure. So actually, if you look at real life, if you want to get this data, usually you will have, for instance, a double bus test setup where we will vary the voltage and the current, and we will analyze the waveforms to extract the loss data. And what we can do here, it's actually exactly the same thing. So we can write a small Python script where we will do a parameter sweep. We can play with the voltage, we can play with the junction temperatures, we can play with all the parameters that we want, like the gate resistance. And we can simulate actually the models from the manufacturers that are based on physics. And we can run it on a customized double bus test circuit, exactly like we will do in real life. But we can also do it with a custom circuits like this. And from that, we can actually, exactly like we'll do in real life in the lab, extract the loss data table. And we can calculate the energy as a function of the voltage, the current, and the temperature, and the conduction losses as a function of the current and the temperature.
Okay, looks great. So thanks, Manu. So let's please accept this challenge. Let's consider the last use case of zero voltage switching operation with an LLC converter. So the first thing with this topology you may know is that as the load current is lagging behind the voltage, when we switch from positive to negative voltage, this switch event occurs with negative load current, which means that provided a sufficient time, that the high side subdiode switch will turn on, and thus with no losses. This is what we call a zero voltage switching operation. But the need for custom data is following. Just before this high side diode switch turns on, the low side switch has started its turn off with a charge of parasitic capacitor series. The turn off current includes a charge current, IOSS, which tends to overestimate a little bit the turn off losses. Well, in hard switching, this is not a problem, as this energy will be lost at the following turn on, actually. But in zero voltage switching operation, this energy stored in SOSS can be recovered at the next turn on, as we can see with the discharge of the high side resistance capacitor to the input voltage sources. So that it means that in zero voltage switching operation, turn-off losses could be lower than the one we got in the double bus test. So, so with this example, now what is the first step? So as Annie already told us, the first step is to generate loss data in zero voltage switching operation. So that's why we wrote the Python script, which sets the different conditions of the test and runs many simulation of the circuit, which reproduce the condition of the zero voltage switching operation. And so let's have a quick look at this circuit with Manu.
Yeah, thanks, Guillaume. So this circuit is actually pretty simple. We have a switching leg that is modeled in SIMBA. We have here the DC bus voltage, we have the semiconductors, and we have the load, which is lagging current source, AC current source. And here in this Spice Netlist block, we actually get the exact model that we get from Infineon for that SiC MOSFET, 1200 volt SiC MOSFET. So here we just went to the Infineon website, we download the files, and we import it in SIMBA. That's it. And with that, we can actually generate waveforms at different current and voltage temperature. So here we have the current and the voltage in the MOSFET. And from here, from the transient, we can actually, by integrating the product of the two, calculating the turn on and turn off energy. And also we can use it to estimate the conduction losses. So, and this basically allows us to quickly get all data, or loss data for different current and temperature, and especially the switching losses in ZVS operation, as Guillaume is going to show you now.
Yes, indeed, Manu. So this graph here shows the total switching energy loss depending on current for two temperatures, 100 and 170 degrees. So, of course, these data can be compared with the ones that can be found in the datasheet in order to check if we have the same magnitude order. And so here, for example, we can see that it is the same magnitude order. So for example, for current of 100 amps here, we've got a switching energy, total switching energy, which is a little bit 0.5 millijoules, whereas for the classical double bus test and the data which were found in the datasheet, we've got an energy which is around 1.2 millijoules. So now it's time to use this loss data in the design modeling of our LLC converter, which here use ideal models with these loss tables. And so as this model is much faster, which can include different parts, such as the control parts or even a municipal part if we want. Okay, and so this simulation of the circuit with the new thermal description gives the following results. So here in yellow, we can get the current through the resonant conductor, and in blue, the instantaneous conduction losses. So here, with these waveforms, we can clearly see, okay, the turn on of the switch and the connection of the diode during the dead time, which shows here poor conduction performances. And here are the switching energies obtained. In green, we have obtained with the data we have generated, which are well smaller than the results. In brown here, with the data of the double burst tests. So to conclude, I would say that this is a typical example of a design process which tries to get the advantage of each power switch model without their drawback. Let's say a SPICE model to get custom power switch loss data, but run on simple circuits so that it can be very fast and you can run a lot of simulations. And on the other side, an ideal model associated with custom thermal description, which is much faster to simulate and can include different parts such as control, magnetics, and so on.
Thank you, Guillaume. Before we wrap up this session, I wanted to give you a quick overview of what's coming next in SIMBA for 2025. So the first area where we will work hard is on the user experience. We think that over the years we have added a lot of features, and now it's the time to actually spend a little bit of effort on the overall experience by using SIMBA. So we are actually working on the results tab, making it a little bit more easy to use, also on the wiring in the schematics. So that will be our main actually focus for 2025. And we have, yeah. The second thing that we are working on is a co-simulation standard called FMI. I don't know if you're familiar with this, but this basically will allow us to connect with tools like Simulink or with basically almost all the simulation platform out there. Magnetics, we have started to work on the magnetics, and we will continue this year by adding loss models and by adding more nonlinear models like hysteresis. And we hope to work with Alfonso from Open Magnetics on this. And of course, we have a lot of surprises and a lot of other features that we're working on and that we cannot disclose for now. So talking about surprises and gifts, I would like to announce that we offer a 15% discount on all new SIMBA license for all the orders placed in 2024. So if you're curious about SIMBA, just go to simba.io and you can try it. And if you like it, then you will have a 15% discount. And yeah, that concludes our keynote. So thanks a lot. We'll continue the session. If you have any questions, please feel free to type them in the chat.